Okay, well, thank you for coming to our special Condensed Matter seminar. Our speaker today is Professor Ali Yazdani from Princeton University. Ali got his PhD, where is it? Yes, PhD at Stanford. I knew that. Working with, I just wanted to verify, working with Aaron Kapotolnik. He did a postdoc with Don Eigler and IBM Almaden, and was then on the faculty at the University of Illinois in Urbana. And since 2004, he's been on the faculty at Princeton University. Ali's early work was on the superconductor insulator transition in thin films of molygermanium, if I remember. Then at IBM, he did some very beautiful work detecting, was it IBM? Yes. detecting impurity states in superconductors. He also did very nice work on one-dimensional electronic transport in nanotubes. But his main focus in the last 10 years has been doing Skynington microscopy on high-temperature superconductors. He had a number of fundamental experiments, I think including one of the very first measurement of finite temperature microstructure and ordering in the high-temperature superconductors. More recently, he's also done some very beautiful work on heavy fermion compounds, detecting the formation of the Kondo resonance and the change in and the shape of the Fermi surface in a heavy fermion compound near the onset of antiferromagnetism. And today, he's going to tell us about his ideas on topological, I guess the word I remember is topological quantum states.
All right. Well, thanks very much, Suvir, for that nice introduction. It's a pleasure to be back here. I've been fortunate to have visited you guys a few times, so perhaps you've heard me give a few talks here on several different topics, including heavy fermions or high TC. So it's nice to be back here. And today I'm going to talk about topological insulators, and actually the subject of topological quantum states in general. So I'm going to start this, treat this as a bit of like a colloquium, give you sort of an introduction to the subject of what are topological insulators, and in general, topological states which are defined by their boundary states that defines them. And this is a subject that has been going on in physics actually for quite a long time, but it's of recent have been of quite of interest because of a realization that now we have a new class of insulators different than our ordinary trivial insulators that are topological in nature. So what I'm going to show you today is that these topological systems have boundary states that have protected properties. I'm going to show you how we do experiments which can actually test some of these protected properties, in particular having to do with how electrons scatter when they live in these topological quantum states. So one of the unusual behavior they have is that they don't backscatter. They don't make any U-turns, which is something very unusual. And I'm going to do something that I don't usually try to do in talks, which is talk about really ongoing research, which is not published at all. And I'm going to tell you about ideas we have in which we're trying to look for topological superconductivity, sort of the next step in this topic. And they have their own boundary states, which are known as Majorana modes. And I'm going to talk about experiments in which we're trying to use artificially fabricated structure to create, if you like, unusual superconducting states. And I don't think I'll have time, but if there was time remaining, I can tell you about, there are even wider classes of topological states having to be protected by, for example, other types of symmetries. So the topic of topological insulators really is fundamentally related to the quantum Hall effect, which is when you have a two-dimensional layer of electrons subject to a very large magnetic field. You're not used to thinking about the quantum Hall state, if you like, as an insulator because it has a Hall current. But you can kind of think about electrons in the bulk of this sample experiencing an energy gap having to do with the Landau quantization, and basically electrons going nowhere like you would have in an insulator. Now, what we know through the work of many is that these states are basically characterized by their boundary properties. So it's true that you have a bulk gap deep inside this 2D system, but at the boundary of this state, you have current carrying state. We have actually chiral properties. So there's been an effort for, I would say, 20 years to try to realize these states in zero magnetic field and at room temperature to see if you can create such quantum Hall states in absence of a magnetic field. So an obvious way to think about doing that, of course, is to think about what the spin-orbit coupling would do to electrons. So through the work of many people, including Charlie Kane and Sucheng Zhang, we've come to realize that there are actually two types of insulators. So this is your garden variety insulator. You have your chemical potential in the gap between conduction and the valence band. Now imagine that I had a knob in the lab that I could turn up the spin-orbit coupling. And I had a way in which I can turn the states that were once conduction band into the valence band, and those that were valence band state into the conduction band. Now, I still have an insulator, but I have created this twist, if you like, in the electronic structure of the material. Now, if you think about sandwiching this sample in between another sample which has a larger energy gap, you can't really get rid of this twist very easily, if you like. And this is the basic idea of a topological insulator. You have changed the order in which electronic states appear from that of the atomic limit, if you like. And you have done this in a way that you can also actually determine if you went to the band structure of this material and look at the parity of the electronic wave function. And a whole host of theorists have shown us basically how you can determine how an insulator is of the topological type or of the trivial type. Now, what's interesting about this twist is, of course, it can't be undone. You can think of that twist, if you like, also as the energy gap associated with the semiconductor having changed sign, if you like. And here you have a situation where inside the material you have an energy gap of one sign, and outside you have an energy gap of a different sign. Now, this is a situation which happens a lot in physics. You can think about that gap being associated with some sort of a mass. And the mass changing sign is something that has a long history of its own. In the physics, in condensed matter physics, you can think about work on polyacetylene. In quantum field theories, there are examples of people thinking about this. And of course, what's special about this is that this basically localizes zero mode, if you like, at the place where you have this twist in the band mass. So these boundary states is what makes a topological insulator different from a trivial one. And it's these boundary states that have topological protection. So how do you look for this experimentally is obviously you look at the electronic structure of the material. And of course, you have a gap associated with being a semiconductor or insulator. And you look at the boundary states, which will appear in energy momentum structure inside that gap. Now, there are many classes of topological states. The one that are generated by spin-orbit coupling and protected by time reversal symmetry will have the property that basically you are forced to have the states cross one another, add basically time reversal point protected plate like gamma equals 0, k equals 0 in the band structure or at the boundary of the zone. Now you have two ways in which you can do this as is drawn here. And this is the way in which you distinguish a topological insulator from a trivial one. The one that has its basically surface state arranged such that you can place the chemical potential to avoid them, or you can connect them in this way and gap them by some sort of perturbation, are the one that are basically trivial. These guys will have to be protected because these points and these points cannot be avoided, if you like. And for that reason, when you cross the chemical potential to this band gap, you always cross these surface energy states, and you can never get away from them. Okay? Now, the added benefit of having generated them with spin-orbit coupling is the fact that the electron's momentum and spin are coupled together. Okay? So what that leads to is this very unusual electronic states are living on the surface of an insulator. So it's a compound which is insulating inside, but electrons run around on its outside. They have their momentum and spin locked together. So obviously you realize that if you cannot have an electron that's moving forward, scatter, and go backward unless you have break-in time reversal symmetry. Another way to think about this is that if you haven't broken time reversal symmetry, in a system where you have a spin-orbit coupling, when an electron encounters a defect, basically it has two options of backscattering. And these two options have to do with the way in which it brings its spin, if you like, around this impurity when it's going forward to going backward. And these two ways basically give you perfect destructive interference. So this is one of the things that had been predicted out there after the discovery of topological insulators. So the first thing I'm going to tell you about are experiments which test this idea to see if this actually happens in an experiment. So how do we do this? Well, we use a scanning tunneling microscope, which, let me just remind you, you bring a sharp tip next to the surface to tunnel between the tip and the sample. You raster the tip across the sample. Typically, you keep the tunneling current constant, and you record the trajectory of the tip. That gives you an image. But usually what we use it for now is to look at what electrons are doing in the sample is measure the rate at which the electrons tunnel between the tip and the sample as a function of energy. And of course, the power of this technique is you can do it as a function of position. And you can basically interrogate what electrons are doing both as a function of energy and as a function of position in your sample. And I'm going to show you a lot of movies which basically looks at, if you like, the square of the wave function as a function of energy of the electronic state in your sample, and analyze what the behavior of electronic states are from these type of data. Okay? So these are basically energy resolved maps of the electronic states in the sample. So let me show you such a map just looking at an ordinary surface electronic state. This is on a piece of copper. What you're looking at is a piece of copper intentionally basically dosed with a few CO molecules, which appear as dark dots here. And what you're looking at is basically standing wave of electrons scattering from defects. Essentially, what you're looking at is the process of backscattering. So if I took a Fourier transform of that image, essentially it shows you that if you're living on a circular Fermi surface of the copper 111 electrons, which is pretty much a free electron gas, you basically are exploring equally this entire Fermi surface. And if I change the energy, this circle basically changes size, giving you a way to also map this Fermi surface. But most importantly, what it's telling you about is about the allowed scattering in the problem. OK, so what about looking at a topological insulator? So I'm going to show you an experiment on bismuth antimony first. This is a compound that, remember, you need a band inversion to create a topological insulator. So Charlie Kane and Jean Mellet and their co-workers realized that if you look at bismuth and antimony, they actually have this band inversion that I spoke about for you already happening. Just Mother Nature gives that to you by turning out spin-orbit coupling. And basically proposed the idea of making an alloy. And this alloy basically has the benefit that you can tune the chemical potential and put it in the middle of this inverted band structure, in the middle of this gap, making you a topological insulator, which was first done by Bob Cava at Princeton. And my colleague Zahid Hassan used the photoemission spectroscopy to look at how electrons move on the surface of this compound, and basically looking for the two signatures, one of them having to do with the odd number of crossing of the chemical potential crossing the bands of the surface electron, and the other one having to do with the spin basically being textured of the electron spin and momentum looking like they are locked at least in the center of the zone. So we set out to look at this compound. So remember, we take the STM. The way we look at these samples is these easily break, and you can expose them to basically an STM operating at low temperatures. And you can go to every pixel, every location on the sample, and measure the rate of electrons tunneling into the sample, and use that to basically build a movie of what the electronic states look like in space as a function of energy, and basically take a Fourier transform of that to look at what are the possible wavelengths that are involved in making the picture that you're looking at. Now, if you do that very carefully, you notice that this is the real space data, which is kind of hard to discern. that there are changes clearly. This is of the same area of the sample, looking at electrons at the chemical potential above and below. But now if I showed you the Fourier transform, you can see that there are very distinct changes in the way the electronic states of this sample Fourier transform. And basically what you're looking at are all the ways in which electronic waves can interfere with one another in real space. So this kind of perhaps looks hopeless. It looks beautiful, but it looks somewhat hopeless in trying to figure out what the electrons are doing on the surface of this compound. To figure out what's going on, let me remind you that these electrons live in an energy momentum landscape, which we can measure from angle resolved photo emission. So this is what the constant electronic density of states in K space looks like as a function of Kx and Ky at a particular energy. So these are all the allowed value, if you like. This is the Fermi surface of this surface state. So the holes are in the center, yes. So if you're an electron or a hole living on this Fermi surface, basically you can explore it by basically scattering from the alloying defect that I have put in the sample. So you might think that if I have such a possible way, all these possible ways of scattering electrons in this sample, if I equally explore it as a function of the momentum transfer Q, I can just basically convolve this data with itself and compare that with what the STM data is telling me. And if you do that, this doesn't look that promising. There are some certainly connections having to do with crystalline symmetry, which is already here. But what you have forgotten to put in here is the fact that the electron's momentum and spin are locked together, which you can easily add in here. But this spin texture is actually quite special, because if you go from the center of the zone to the zone edge, basically you have a situation in which you have a handedness, if you like, to the material. There is one going circling one way, the other way, and there is one left behind at the end of the day. So this is actually the definition of having a topological surface state. Okay? Otherwise, from spin-orbit coupling, you could just simply have an even number of those, and that would not be topological. Okay?
Where did you get, what does the radial dependence come from?
So where did I get the radial dependence? Why this is going this way and that's going the other way?
Yeah.
So basically, So we knew from photo emission this one was going one way and that one's going the other way. We didn't know anything about the other circle because that's not basically measurable from the photo emission experiment. But we know that this is a topological insulator from the band structure calculation. So we make the assumption that this has to go the other way. Otherwise, we don't have that information. And in a sense, that's what we are testing in this experiment. So if you put that into the data, you also have to look at the way in which the spins are allowed to scatter. Obviously, you cannot scatter from this state to that one. If you include that, you see that you start to match the experimental data in all its great details. So let me zoom in on that. So these are the high symmetry direction in the data. The reason these are interesting to us is that these are basically telling you about wave vectors in which you can scatter, if you like, from an electron that's moving forward to an electron moving backward with the same momentum, but now it has to have the opposite spin. And you can see that those wave vectors, which you might have expected to be in a simulation, are basically missing in the experimental data. But if you put in the spin texture and basically run this sort of simulation again, you get all the little details that this data produces.
So your impurities are short range impurities, so
exactly.
They can transfer momentum from one valley to the intervalley scattering.
Yes. So actually, this question of what the range of the potential is will be very important, and I'll show you that in a second. That actually has an effect that is actually quite important.
Impurities don't flip spin.
Well, in this case, we don't have anything magnetic in the sample. So bismuth antimony is...
There could be spin-orbit coupling and things.
Right. So this is actually one of the ways in which so time reversal symmetry is not broken here. So that's basically what this experiment is showing us, is that this signal is missing because the impurities that you have here are non-magnetic, and that's what you would expect from this spin texture of the material. So I won't bore you with the detail, but those...
You're saying it doesn't matter what they are.
No, it does matter if they're magnetic or not.
Right, but as long as they don't break time reversal symmetry, but they have
Well, the impurities in this sample do not seem to allow any scattering between K and minus K. Let's put it that way. Okay? Now, you can imagine situations in which I believe you have to break time reversal symmetry. I think there is no other way. Okay? So I won't bore you with the details of trying to understand this beautiful data based on all the allowed scattering and the disallowed one. I just want to make one point, which is that we can do this in very high precision. Namely, we can look at the measurement of the electronic Fermi surface as a function of energy, and using this model in which we take into account the spin texture, we can map basically the simulation to the experimental STM experimental data with very high degree of accuracy for the places below the chemical potential, which there is information from angle resolved photo emission. So this is the comparison between model and the experimental data. So what this establishes is the fact that you have no backscattering in this particular compound. But let me say that the number of topological insulators now has grown to many, many. There are hundreds of compounds. And nowadays, the focus are on those topological insulators, which the structure of the electronics of the surface state is very simple. In particular, is Dirac-like E versus K behavior. So instead of having 3 or 5 crossings, here you just have one crossing in the chemical potential. And again, you have the same spin texture, if you like, associated with the electron momentum being locked together. Now here, actually, it's very difficult to establish experimentally, as you'll see in a second, whether backscattering is forbidden or not. Because if you look at this electronic structure of electron at some constant energy, the set of wave vectors, a set of scattering processes that are forbidden is a set of measure 0. It's only K going to minus K that's strictly forbidden. All the other wave vectors are allowed. But nevertheless, you can test the idea actually at higher energies. So here is the Fermi surface of bismuth telluride. There is very similar data on bismuth selenide. This is an anisotropic E versus K behavior as a function of Kx and Ky. And when you do the interference experiment on this sample, you also see a great deal of real space structure, which in momentum space gives you very beautiful data, which is related to this Fermi surface. What's satisfying about this is that you can actually image electrons basically having this linear energy momentum dependence all the way down to the Dirac point on the surface of this compound using the STM. Now here, it turns out the same idea basically works. You have a Fermi surface that looks like this. And you can ask, how can I understand the STM data? Again, you can take into account, forget about the fact that you have any kind of forbidden scattering, and just think about all the allowed ways that you can scatter. You get something that doesn't look like the STM data. If you add in the spin texture, you do a little bit better. But actually, you find that you don't quite get there. And this has to do with the fact that because there is spin-orbit coupling, when the K states have curvature that's basically shown as this snowflake structure shows, you actually have a slightly different spin signal, as well as in plane. You have a slight out-of-plane signal that actually oscillates around the Fermi surface as you go around. And this turns out to be a key factor to include basically in your scattering wave vectors in order to actually match the experimental data. So here's a situation in which you have a 3-dimensional spin texture, if you like, that's really, really restricting the possible ways you can scatter in this compound. Now this goes to your question. I won't spend a whole lot of time on it. So what I've been focusing on are scattering from basically short-range potential. And of course, there's no backscattering, so people might think, oh, these states can basically go through material without any kind of electrical resistance or any impediment but impurity. But in fact, what you find experimentally is that when you have these materials, many of them are basically doped semiconductors. So doped semiconductors have a situation in which you have fluctuation of the electronic band structure as you move around the sample, created by basically dopants. And in fact, you find that the whole electronic structure in the material is fluctuating in real space. And we find that, in fact, the electronic states of the surface respond to this potential by basically changing their wave vector continuously as you move around the sample, basically riding this disorder potential having to do with the dopants in the sample. Okay? Now, what's interesting here is that this disorder potential is very important for these electrons as you get very close to the Dirac point because the wavelength gets very long. And here you have scattering wave vectors, which is basically this is showing you that the scattering wave vectors become ill-defined as you get very close to the Dirac point in this compound. And this is because of the disorder potential in the sample, and it has major consequences for the transport through this electronic state. Yes? No, actually, what happens is that I glossed over this a little too fast. If you break up the sample in different regions that are corresponding to regions of basically potential being high or low, you can take a Fourier transform, and you can find that the Q vector is actually very different. And what you find as you make the samples cleaner, this distribution of the wave vectors becomes sharper and sharper, and this difference between electrons moving in the high potential or the low potential start to match together closer and closer. So this distribution of wave vectors is really associated very nicely to the disorder potential having to do with the dopants in the sample. Okay, so now they don't backscatter. They do move through smooth potentials. So what do they do if they come to the edge of a cliff? Okay, and this reminds you of Thelma and Louise. What was the name of that movie? So let me tell you what ordinary surface states do. So you can think about taking a crystal and just looking at a single atomic step. Okay? These are surface electrons on copper. They basically scatter, make a standing wave, and you look at the phase shift, and you'll find that basically almost 80% of the time they're coming back to you when you hit an atomic step. And 20% of the time they're lost to the bulk. They're gone. Okay? So we did an experiment on antimony. Now antimony, remember, has this inversion associated with the spin-orbit coupling that I told you about at the beginning of the talk. Now, it is a semi-metal because conduction and the valence band sort of overlap one another. But as far as the surface electrons are concerned, these are topological surface states. And what we did is the following experiment. We have an experiment in which we have a very large terrace and a very small one, okay, in which you're basically looking at electrons basically scattering from this small terrace. And the question we had for us was that we had done experiments like this on ordinary surface states. We always saw that basically there's basically no transmission through this small terrace. Okay? This is kind of like a Fabry-Perot interferometer. And if you look very carefully at this, okay, so there is a slight difference between ordinary electrons for this antimony because they are topological, the standing waves you see are made out of not K and minus K, but K and K prime where they have the same spin structure in the sample. Okay? So what you see here, if you focus in on the data, so what you're looking at is energy, and the colors represent the square of the electronic state as a function of basically how much electronic states you have at a particular energy as a function of position. And what you're seeing is basically resonances inside the little box, and out here, standing waves that basically have a phase shift associated when they come resonance with the box. This is almost like an undergraduate, freshman physics experiment, okay? Except it's done with topological surface state. And you can look at this pattern and look at the intensity in Fourier space of these waves and look at their intensity as a function of energy, the amplitude of the wave basically as a function of energy out here on the big terrace. You can clearly see that there are these dips. And if you remove that background, basically this becomes your Fabry-Perot interferometer, from which you can extract basically the transmission through this very large barrier having to do with this atomic step. And what is surprising here is that we can, of course, get the reflectivity of the electrons looking at the electrons inside the box. What is surprising here is that even though you're looking at an atomic step, which is a very large perturbation, electrons are just as likely to reflect into the same spin state or go forward in this material onto the next terrace. So what this experiment basically showed us is that unlike ordinary surface state, what happens to topological surface state is that they are connected between the different terraces of the material. So if you put an electron in one terrace, there is a likelihood that it will leak out and go to the next terrace, which is something we've never observed with other surface states. OK. So what's next? So that was perfect. I sort of covered a lot of material here having to do with this protectedness of these topological surface states. So one thing you can do is you can try to control this property, this protectedness. And the way you can do that, for example, is by introducing time reversal symmetry breaking with magnetic impurities. Or the experiment that's going on right now in the lab is to put islands of magnetic material on the surface and basically manipulate the spin orientation of this island with a magnetic field to basically break the symmetry, introduce backscattering, which will also gap these topological surface states. So there would be a way in which you can manipulate these surface states if you can break time reversal symmetry using magnetic perturbation. So let me move on to the next topic that I'd like to talk about, which is topological superconductors. So this is actually a topic that has been going on for quite some time, having to do with conventional pairing in superconductors. And now, because of topological insulators, there is this a new connection with this field. So what would be a topological superconductor? Basically, with analogy with topological insulator, you have a situation in which the bulk of the sample is gapped, but the electrons live on the surface of the sample, which are not gapped, okay? Just like surface states of a topological insulator. This has a connection to a lot of different physics, and the reason it has this interesting connection has to do with the fact that because of superconductivity, the edge modes of these topological superconductors would be what's called Majorana fermions. So many of you know what Majorana fermions are, but let me just remind you that these are real fermions. That would be their own antiparticle, and this is what makes them very special. Okay? And in a condensed matter context, the way you would go about perhaps engineering a system which has Majorana fermions always would involve superconductivity, because you basically superconductivity mixes with for you electrons and holes through the gap interaction. So we are all desperately seeking ways of making Majorana fermions, and let me try my hands at trying to explain to you what's the connection between this and the subject of topological insulator. So one is this connection having to do with the fact that you have a system which is gapped in the bulk and it has boundary states. And perhaps nothing shows this nicer than a very, very simple model, which was first proposed by Kitaev, in which imagine you have a system where you have a number of sites, okay? And in this system you have superconductivity, but the superconductivity is a little bit unusual in the sense that you usually think about pairing electrons on the same location in the sample, spin up and spin down. Imagine here your superconductivity is with particles that don't have spin, okay, which is a little weird, but you'll see what the connection is in a second. And imagine the superconductivity makes pairs on nearest neighbor sites. Okay. Now, this is not undergraduate physics. I think it's first-year graduate physics. Maybe they're filming me, but I'm planning to put this on my final exam in my graduate solid state. Because what you can do is you can take this Hamiltonian, which allows Cooper pairs basically to be formed like this and move along the sample. And if you introduce the idea that you can have Majorana fermions, which are basically splitting the electron into two pieces, Kitaev showed us that there is a phase, which is topological, in which you can pair up these. So an electron would be two Majorana fermions. So here's an electron here, here's an electron here. And you can pair up your Majorana fermion. These are the different sites along your chain in sort of two different ways as it's drawn with these dashed curves here. So this is actually very similar to the idea of a topological insulator. You have a gap in the bulk of this system, and at the end of this, you have these lonely balls, which are basically your end states, which in this case would be Majorana fermions. So this subject is all the rage because actually it's subject to quite a bit of work even also here at Harvard, which people are trying to come up with ways in which you can generate such a chain, the Kitaev chain. So it's called P-wave because the superconductivity is not with pairs on the same site, is pairs on the nearest neighbor site. Now, how do you make spinless paired electrons? Well, if you start with a system that has this topological, this spin orbit coupled in a topological state, so here is the situation which you have electrons moving k with one spin and minus k with another spin, you can basically forget about spin if you like, because momentum already defines for you what the spin is. So in some way, you can think of this as a spinless fermion. And what's nice about this is that if you put this system in contact with a superconductor, you're making a topological superconductor. And the proposals from many folks, Jay Sao, who I believe is still here, is you take a system of either a topological insulator or a strong spin orbit coupled system, which can create for you such an electronic structure in the right situation, like in a field. And you put that in contact with a superconductor. And what is expected to happen is that if you look at the end of this wire, you will find Majorana fermions, which are particles that are their own antiparticles. So if you look at the spectrum of excitation, they show up at the zero bias state in a spectroscopic experiment, because a zero bias state basically gives you an equal mixture of a particle and an antiparticle. You're dealing with what we call a half a state. Half of it lives here, and the other half lives over there. OK. Now, the buzz in this field has to do with this experiment, which is done at Delft. And there is now a similar experiment at Weizmann, in which you basically do what I just described to you with a superconductor and a nanowire. And here's the experimental result that shows a very definite zero bias peak, which has been interpreted as possibly a Majorana fermion. Now, the problem is that there are lots of ways you can get a zero bias peak having to do with disorder in a superconductor. I'll show you some of them, in fact. If you did a Google search, you get 13 million hits. And I think since this paper, this number has gone up maybe by 100,000, maybe not so much.
What do you have to search?
Zero bias peak.
Oh, zero bias peak.
So there are lots of ways. Stay awake, Subi. So what do we need? The problem is you need to find a clean way to do this experiment. So this is what I'm going to tell you about in the remaining time. And this is what is nice about the subject of, for me, for topological insulators, is some of these ideas can be mapped to a completely different regime where it involves no complicated materials, no spin orbit coupling. But the ideas are what you need to. So here's we have a new approach to this problem in which you take a bulk S-wave superconductor, I'll show you an example of, and instead of using spin orbit coupling or topological insulator, you use the spins and their spin texture as a way of mimicking basically handedness in the problem. As I will show you, this actually, in the modeling we have done, actually shows this to be a very promising route. So before I do that, let me just describe to you what an impurity does to a superconductor. So if I have a magnetic impurity, that's when things happen. Non-magnetic impurities don't do anything to a S-wave superconductor. A magnetic one, if you like, simply put, attracts one of the spins. It breaks Cooper pairs. So you can think of this as sort of an attractive potential for one of the pairs. More precisely, you can do a calculation where you add the exchange interaction to the BCS Hamiltonian. And when you go turn the crank, you get electronic states that live at low energies inside your gap of a superconductor. These are called Shiba states. So this is the gap of the superconductor. Inside it, you get states. And these states, where they are in energy, depend obviously to the strength of the exchange interaction between the spin and the Cooper pairs in the problem, or the electrons in the problem. Now, you can actually detect these. I did this experiment many years ago. And here's it being repeated now in my lab. Here's the surface of niobium. Those are individual, which are these? These are manganese atoms on the surface of niobium. You can make niobium even cleaner than this, but this is pretty good. And what this is basically looking at the density of states, focusing on states inside the gap, basically showing you how when you go near a magnetic impurity, you have basically states that live at low energies. Okay? So these are those bound states to this impurity coming from the exchange interaction. And it depends what atom you put there. If you put manganese, you get states at different energy. Okay? And the details don't matter. We actually understand this in great detail, these data having to do with just exchange interaction of a spin impurity with a superconductor.
Ferromagnetic or antiferromagnetic?
These are single spins. So,
What was the coupling to the conduction electron ferromagnetic?
oh, it will happen in either case, yes.
But do you know the sign?
No, we know the size because we can match the state's energy. Well, what's important is that we can map them in real space. And this is where they live. They live around these impurities. They're very short range. Okay? Okay, so what does this have to do with Majorana's? So we built a chain of these impurities. Okay? And what you have in this chain idea is that you have ability for the electrons to hop from impurity to impurity. That's this term. You have some local exchange interaction, which I just told you about. And of course, you have superconductivity, which is being proximatized, if you like, onto that wire. Okay? Now, this is where you turn the crank and you calculate what the electronic states of this system is on a lattice of, say, 40 by 40 atoms. Okay? You solve what's called the Bogoliubov-de Gennes equation. And you find that, OK, if you look at the energy of the excitations in this system as a function of what the strength of the magnetic interaction is at each of these sites, you find that as you turn up the exchange interaction, basically the first excited state comes down. Okay? And at some point, basically, you end up with the states that living at zero energy. Okay? This is where you get a topological superconductor. So this is a very, very simple problem. I just have a chain of magnetic atoms on the surface, okay? And I'm glossing over one detail having to do with the spin texture, which I'll get back to you or talk to you about if you're interested. But what's interesting about this model is that it needs only something like 20 sites, okay, in which you can build this chain. And you can compute from this calculation when you're in this range of parameters. Now, how can you change the range of parameters? Well, one of the things in the model you can vary, which you can vary in the experiment, is the distance between the impurities, or what you use for impurities. But none of that matters in the sense that we can find in the model where we can be in a topological phase and a non-topological one. And we can just look at the excitation spectrum and look at what the excitation spectrum looks like. And the first excited state, when you're in the topological phase, is clearly living at the edge of the system. And you can actually check this for the expert in the audience by looking at what's called a Pfaffian and so on in the calculation. So we are setting out to do this experiment. Oh, so here's a bit more details on that. So what you're looking at is a state that lives right at the edge of the wire with only 20 sites. And it's very clearly inside is some sort of a gap which has to do with an induced P-wave gap on this wire, which I won't go into the details, but you can see that there is a very nice zero bias peak coming from the calculation. OK. So how do we do this? So, well, that's one of the powers of the STM. You can actually fabricate structures using the STM. We have done this, for example, with other kinds of spins like spins in semiconductors. These are experiments done a few years ago in which we actually put spins in gallium arsenide and watched them interact with one another, just spins at different distances relative to one another. So this experiment has gone on the way, and we are basically building structures in which we can study the interaction between these spin impurities by building structures with different number of atoms. And what we find is that indeed, if you look at these states, as you couple them together, you start to change the nature of the bound state. You can get the state to move closer to zero. You can split these states. And the details are still being worked out. But experimentally, what's promising is that you can clearly see changes and interaction between these localized states when you bring the spins close together. So this is our first step. And of course, we jumped ahead and made some chains. And OK, I'll show it. So it's not surprising, but it shocked us. But that you can see zero bias peak, and actually it does appear to be with very short chains. You can see it at the ends of the chain. So there is data coming, and this is just I thought I'd show you some very rough stuff. But let me tell you what's the advantage of this technique. So obviously you can make very clean structures. You can make crystals of niobium. Niobium is actually difficult. Lead is probably a little easier. Very, very clean. And you can assemble chains up to 20, 30 atoms, no problem. And of course, the power of what we are doing is imaging. We can go at the end of the chain and make sure this zero state is really associated with the end of the chain. But what's kind of fun is that now you can imagine to really do tests, which really shows that this object is a Majorana. So what are some of the tests you can do? For example, if you bring two Majoranas close together and you couple them together, they will basically split, if you like. They annihilate, if you like. So you can actually demonstrate the symmetry of these states by basically building coupled chains. So if you have two chains, it should go away. If you build three chains, they will come back. And all within the reach of the experiment. So there is a challenge which I didn't want to get into, but it has to do with the spin texture. And this spin texture is critical, but we have ideas in which you can perhaps explore not just linear chain, but zigzag chains in order to create a handedness to the spin that's as I've drawn it here in the experiment.
The data you show has a spin texture.
So we just did this experiment. We just made gadolinium chains,
Yes.
and we find a strange effect, which is that in the middle of the chain there is a gap. On the edges there are these peaks. So we don't have any spin information about what the spin is doing here. So this is very, this could be anything, but it's very promising because it lives at the end of the chain.
But the calculations you showed, you already had a spin pointing.
Right. So that's what I mean. The spin texture is. So it turns out. Okay. So the idea is this, and you can find this in the calculation. You need some finite angle between the spins, and you can think of this in the following way. What we are trying to make is a p-wave pairing, nearest neighbor pairing. So imagine you're a pair of electrons. You're trying to hop into two nearest neighbor sites. If the two sites have their spin anti-aligned, it's great. You can hop onto that site, but you won't go anywhere because it's spin blocked if you're antiferromagnetic. Of course, if they're aligned like this, you can't get on as a pair like that unless you're a triplet pair. So as soon as you count the angles away from being up and down, what you have is a situation in which you can have Cooper pairing on nearest neighbor site, and they can run along that wire.
We need some kind of spin orbit like Zelensky-Maria.
So that actually favors having spin texture in a lot of 1D systems, like
That's my
Sure.
question.
Yeah. So
Usually spin orbit should be strong enough to produce topological system.
So
What should be the similar parameter in your system?
so it's what should be the
Yes, and to be analog to spin bend inversion.
So I understand what you're saying, and to be completely honest, I don't know, because we are just running this simulation to see whether this model does have analytical solutions if you take it to a one-dimensional, you integrate everything out and you just do it one-dimensional. So I don't know exactly, but it has something to do with the pitch of this spiral. Okay, so it's perfect.
Maybe I could.
So the question was whether you can really make it perfectly. You can. I mean, it's just when you're talking about a landscape of 20 by 20 angstroms, you take a crystal, you can make it beautiful, every atom in its place, and you evaporate these atoms when the sample is cold. You manipulate it with the STM, and you can really build a chain with a very high precision. It's not a problem. Which is the reason I'm telling you this, is the reason I'm excited about it, is that you need 20 sites. And this actually is related, I don't know if Jay is here. Jay South, he did a similar model which he did at quantum dots where just 3 or 4. So you don't need many to produce these topological states, which is sort of surprising.
But,
That's the one thing that I don't know how to control. So one thing I have, what we can try to measure it using spin polarized STM, and what we would try to do is make zigzag chains where we will frustrate any interaction they have in order to get a finite angle between them. That's what's required in the model. You need an angle. That determines for you to have this sort of unconventional pairing on the chain. If you don't have an angle, it won't work.
when you say about experimental data, of course.
Well, so these are the tests you.
When you say about the model,
That's the model.
then in the model there should be either exchange only, or something like the Lashinsky Maria. So whether in the model.
So in this is just a local field. There is there is. I think if you're asking self-consistently, what's the spin texture of this chain, that I have not told you anything about. But there are many examples which you can find that 1D chains basically make spin textures experimentally. Right. Okay, so I think I've kept you enough for long. So these are, there are many examples of now these topological states which are defined by their boundary states. So I showed you example of the topological insulators where we are going towards, and many of them have protection from backscattering for one reason or another. For example, I didn't have time, but there are now new classes of topological surface state protected by mirror symmetry, which is not time reversal symmetry. And those are also have their own protection having to do with the fact that unless you break the mirror symmetry, you can't have any backscattering. We're working on those to try to basically test out whether these symmetries actually protect the state. But these artificial systems, whether they're nanowires or atomic chains like the one I described, one way in which you can perhaps take ideas from this field and try to simulate them in simpler materials. That's one way direction we're very excited. So this is the most important slide of the talk, is basically who's done all the work. The folks on top are folks that were either in my group or have just recently moved on to other jobs. Pedram Roshan and Anthony Richardella did their thesis on topological insulator. Chaim Beidenkopf was a postdoc, and now Weitzman did the work on looking at these long fluctuations of Dirac electrons. And this is the new crew, and Stefan is the one who's working on chains. And we really got a lot of guidance on how to do this simulation and from Andre Bernovic. And of course, none of this would have been possible working without materials people who we've been collaborating for over the years. So I stop there, and thank you for your attention. Maybe you should pass this along.
Oh, okay. The courtesy of John, though. Anyway, we have time for a few more questions. Yeah.
You mentioned that if you place two like in a
When you basically you split them. Or actually, I don't.
How close should be?
Okay, that's a very good question. So one of the things that surprised us in these models, and also it bears in the experiments we've done so far, is the bound states associated with these impurities are very short range. In fact, one of the things that may be the advantage of this approach is that you don't seem to need, you don't need to do things on the length scale of the coherence length of the superconductor, which is what the nanowire people are trying to do. So the range of interaction seems to be maybe 20 angstroms, 2 or 3 lattice sites, 4 or 5 lattice sites. So you don't need to place them very far from one another. And that's what the experiments show so far. Okay.
What do you see along this chain, actually, along the edges? Do you still see the gap of the power?
Yeah, no. So what happens is you induce a gap. If you solve it consistently, if you do the experiment, you see, like the chains we have built so far, you see a gap in the middle, which is somewhat changed from that of the bulk, but it looks, it's been reduced. So what you're looking for is a gap that basically is of a different superconducting order parameter. And which is the model calculation shows it. Experimentally, we don't know right now whether that gap is made out of states, or basically we do see a clear gap in the middle of the wire and no clear gap at the ends. But there's much more experiment that needs to be done. The model shows it clearly that when your zero bias state appears, it lives in the middle of a gap. But this is true of all these models that produce the MRI. I assume there is some texture. Pops out. So then I can change that texture in the model and see how sensitive it is, and you can maximize, for example, the strength of the.
So in the model, this is a calculation.
It's a calculation.
No spin orbit. You have exchange coupling, and you put a fixed spin texture.
Yeah, I showed the model. It's very simple.
But in the real world, there probably is some spin orbit.
That's fine.
Okay, sorry.
So let me ask that question. Somebody said that now, in the real world,
In the real world, there is experiment, so the model is irrelevant. Yes. Okay, so what we do know, okay. Yeah, so surface and isotropy typically tends to favor some direction of the spin. So for example, if you put iron on copper, you find 2 spin states depending on where the iron sits. If it sits in the middle, it likes to point up because that's symmetric. If it sits on sort of a bridge site, it will point one way or the other. Well, also perhaps the spin-orbit coupling and perhaps the interaction between them. But these are all high-energy physics, if you like, and they're not relevant to the superconductivity that you're looking at millivolts. What is important is the spins are static, and they have a texture. That's what we find in the model. Where you get the texture from is less important, I think, for the physics at the millivolt level.
But in your model, to get the spin texture, you're breaking symmetry, because you're putting in some definite spin orientation. But once you put in spin orbit coupling, the spin texture is very natural. You're not breaking any symmetry except for time reversal.
Yeah.
So you require to break time reversal or no?
No, it's not. Well, let's see.
The model does.
The model does, yes.
But the actual system probably doesn't.
The actual system doesn't break time reversal symmetry. Why do you say that? I mean,
I don't think so.
I mean, if I put a spin on the superconductor,
yeah.
Which direction does it flip back and forth? Does it stay like this? These are the questions. These are the kind of questions that you're asking about. Yes. They're very.
So what is the coherence time of a spin in all these impurities?
Nobody knows. Never been measured.
Okay.
well, but it's kind of tricky about time reversal. You can have 2 states which are connected by time reversal symmetry. But let's say if you do 9 cup, minus 9 cups, you just never get. You're stuck in one.
Yeah, so you have a very big barrier, so the temperature.
But if you're stuck, then you're broken time reversal. Yeah.
Locally, yes.
Yeah. So you think you're broken time reversal.
Well, I mean, in some way, if even if you're in a single spin, you can say a broken time reversal because I have a bound state. No, that's what there is the spin is pointing in some direction in order to get a bound state.
All right, I think I should let others speak. Okay, yes. Somebody else then. Yes. Not me, sure.
Let's just speak.
But wouldn't you, like, you're assuming that this, like when you place the speeds, they arrange according to some kind of order, but wouldn't some kind of laissez physics appear in this? You know, I would think that there is a lot of orientation.
Okay, so the number of experiments on spin chains, there are a number of experiments on spin chains that I can tell you about that we know something about. So for example, if you build iron on, say, surface of copper, they tend to make antiferromagnetic chains. And there are two metastable states. And this is not results from our group. But how do we know they're metastable? Because you can use a spin polarized tip and image them. But then if you inject some high energy electron, the whole system flips and it makes you the other state. And you say, there is a, so it's a static spin system. So that's not, so what's making that static spin? Well, the connection to the surface. So there are lots of experiments like that out there on metal surfaces by other groups. So it wouldn't surprise me that you would get a very static spin texture. In fact, if you like, these bound state measurements can be used to put a bound on the dynamic of the spin. Because if the spin was not static, then the line widths there will be additional line widths to the thermal broadening. So you can, for example, push these experiments to measure the line width of the bound state as a way of determining what the spin lifetime is, because the bound states are caused by those spins. So you can get some handle on questions you're asking. It's the danger of talking about work in progress.
Small system sizes, can we do some NMR type techniques to sort of manipulate the spin on the surface of the?
So what you need to do those experiments, the answer is probably yes. They're tricky. What you need for those experiments is you need first the spin lifetime to be long enough if you put it in some, say, superposition state, which is not easy to do. STM is a static probe, but there are ways in which you can do pump probe experiments. This is, again, not work by my group, which you can excite the system, watch it relax down. And for example, if you're interested in spin properties, if you have a spin polarized tip, you can detect them. And so for example, T1 has been measured using an STM probe. But T2 has not been measured because you cannot do yet experiments which are coherent manipulation of the spin. For that, you need some RF field, or you need some way of coupling to the spin. And and you also need very low temperatures for the spin lifetime to be long enough. But yes, in principle, yes. These are all possible.
So you mentioned when you can parallel, you can see the Majorana fermion signal again. So I'm just wondering whether this Majorana fermion, do you think is that because two of them are coupled and you see the remaining one, or some great mixture?
It's a good question. I think, you should expect to be, in coupled chains to annihilate, and then the new ones should appear. But, we haven't run the model with 3 chains, and we certainly haven't done the experiment. Like, that would be the experiment to do with this 5-chain system. It is doable. I don't know. I'm sorry.
Okay, well, thanks, Ali, for a very wonderful talk.
Thank you.